Hey everyone, and welcome to This Explainer. Today, we're uncovering a massive climate reality that honestly usually goes completely unnoticed. When we look up at the sky or check our local weather apps, it's super easy to think of the atmosphere as the main arena for global warming. But the truth is, the ocean is not just some passive backdrop to our changing world. It is the ultimate overworked climate buffer. For more than 2 centuries, it has been silently taking the absolute brunt of human emissions, effectively masking just how severe our climate footprint really is. So today, we're going to unpack exactly what that incredible buffering is actually costing the deep blue. Let's dive right in with this statistic that is just staggering. Since 1970, the ocean has absorbed 91% of the excess heat trapped by human-made greenhouse gases. That means the atmosphere, the land, the ice caps, they're all just splitting that tiny remaining 9% slice. Just pause and think about that for a second. If that 91% of heat had gone directly into our atmosphere instead of the water, our global surface temperatures wouldn't just be uncomfortably warm, we would literally be boiling, with temperatures jumping by many tens of degrees Celsius. The ocean's enormous heat capacity has quite literally saved us, but as we're going to see, it is definitely not an infinite sponge. And that brings us to the physical cost of all this buffering, because that massive heat capacity does have a limit. The ocean is fundamentally overheating. We're talking specifically about the upper 2,000 meters of the ocean, which is basically the layer where the vast majority of marine life lives. Temperatures there are increasing at an accelerating rate. In fact, in 2023, the heat content in this upper layer hit a brand new all-time record for the 4th consecutive year. The ocean is taking on so much energy right now that the water itself is physically expanding, which, by the way, is a huge driver of sea level rise, and it's altering massive global ocean currents. Now, this relentless warming sets the stage for some really devastating events, known as marine heat waves. By definition, a marine heat wave is a period of anomalously high sea surface temperatures that cross the 90th percentile threshold for at least 5 consecutive days. I want you to think about those blistering summer heat waves we experience on land. The ones that buckle roads and cause massive power outages. Marine heat waves act exactly like those terrestrial heat waves, just underwater. They're intense, they're classified anywhere from moderate to extreme, and they rapidly stress or even kill incredibly sensitive marine life that simply has no way to escape the heat. And the frequency and intensity of these events, they've skyrocketed lately. Take the period from 2014 to 2016. There was this massive event known as the blob in the Northeast Pacific. It pushed sea surface temperatures up to 3 degrees Celsius above normal, and it stayed that way for over 2 years. The result was absolutely tragic: huge toxic algal blooms and widespread seabird die-offs. We also saw the Mediterranean get hit by record-breaking heat in 2003, and then again with a massive basin-wide event in 2022 that caused extensive die-offs of sea sponges and seagrass. And of course, the heat waves in 2016 and just recently in 2024 pushed water temperatures so high they completely devastated the Great Barrier Reef. But here's the thing, the physical heat is really only half the story. Let's pivot for a second from those physical changes to the invisible chemical cost. In addition to soaking up our heat, the ocean is also our planet's dominant carbon sink. It has quietly absorbed about 30% of all the human-made carbon dioxide emitted since the Industrial Revolution. Without the ocean soaking up a third of our carbon footprint, the buildup of CO2 in the atmosphere would be far, far worse. But just like absorbing all that heat, absorbing all that carbon comes with a really profound price tag. That price tag is a fundamental shift in seawater chemistry, something scientists call ocean acidification. When carbon dioxide dissolves into seawater, it doesn't just sit there doing nothing. It actively changes the chemistry. It reacts with the water to form carbonic acid. That carbonic acid then breaks down and releases hydrogen ions right into the water. And it's those extra hydrogen ions that actively lower the pH of the seawater, making the whole ocean more acidic. Now, at first glance, the numbers we're talking about here look incredibly deceiving. Before the Industrial Revolution, the surface ocean pH was sitting at about 8.2. Today, that current surface ocean pH has dropped to 8.1. I know, to most of us, a drop of 0.1 sounds practically meaningless, right? It sounds like a tiny, marginal rounding error. But we really have to remember that the pH scale is logarithmic, sort of like the Richter scale is for measuring earthquakes. Because of that logarithmic math, that seemingly tiny zero point 0.1 drop actually translates to a shocking reality. It's a 26% increase in the concentration of hydrogen ions. That means the ocean is literally 26% more acidic right now than it was in pre-industrial times. It is a massive, incredibly rapid chemical shift, and marine life just hasn't had the evolutionary time to adapt to it.
And unfortunately, the chemistry doesn't stop changing there. If we look at high-emission scenarios, the surface ocean pH is projected to plummet from its current 8.1 all the way down to 7.8 by the year 2100. Again, it's just a few decimal points on paper, but I really want you to imagine what that actually translates to out in the water.
It translates to this absolutely devastating projection, a 151% increase in hydrogen ions from pre-industrial levels. So by the end of this century, the ocean's acidity could more than double.
So why is this abstract chemistry such a big deal for biological life? It all comes down to a concept called saturation state. See, lots of marine organisms build their shells and skeletons out of a mineral called calcium carbonate. When the water is supersaturated, life is great. These organisms can easily pull the minerals they need right out of the water to build and maintain their shells. But as the pH drops and those hydrogen ions flood the water, they actually bind with the carbonate, stealing the very building blocks these animals desperately need. When the saturation state drops low enough, the water becomes what we call undersaturated. And at this point, the water is literally corrosive. Not only does it become nearly impossible for animals to build new shells, but their existing shells actively begin to dissolve away.
And the victims of this chemical shift aren't just obscure creatures. They're the foundational species of the marine food web. We call them the calcifying organisms. Think about corals, which build their intricate skeletons from a specific type of calcium carbonate called aragonate. Or pletropods, which are these tiny, free-swimming pelagic sea snails. They're sometimes called sea butterflies. In the freezing, CO2-heavy waters of the Southern Ocean, scientists are already out in the field documenting pletropod shells dissolving while the animals are still swimming. Then you have bivalves, the oysters, mussels, and clams we love to eat, and microscopic plankton called coccolithophores that literally form the base of the entire biological carbon pump. The wild thing is, we don't even have to look out into the deep ocean or wait for the future to see this happening. We've had vivid early warnings right on our coastlines. Back in the 2000s and 2010s, oyster hatcheries in the U.S. Pacific Northwest went through catastrophic multi-year collapses. Why did that happen? Because cold, naturally corrosive deep water, which was made even more acidic by our carbon emissions, was upwelling right into those hatcheries. The water's saturation state dropped so low that baby oysters simply couldn't form their very first shells. So this wasn't some far-off warning for the year 2100. This decimated real businesses and real ecosystems decades ago. Section 3. The double assault, heat and acid in concert.
So, while warming and acidification are technically independent consequences of our emissions, they are hitting marine ecosystems at the exact same time. And this creates a virtually impossible situation for places like coral reefs today. It's basically a two-step synergistic nightmare. Step 1, a marine heat wave hits. The thermal stress causes corals to totally panic and expel the microscopic algae, the zooxanthellae, that live in their tissues and provide up to 90% of their energy. This is what we call coral bleaching. The coral turns completely bone white. Now, it isn't dead yet, but it is starving. Step 2, the coral desperately needs to recover and rebuild its weakened skeleton before the next heat wave rolls in. But ocean acidification has already slashed the availability of carbonate in the water. The calcification rate plummets. The corals simply cannot rebuild fast enough in that acidic water. It's a brutal double assault. The heat starves them, and then the acid prevents them from ever fully recovering. Which brings us to the ultimate, really tough question we are left to ponder. The ocean has done us a huge favor by masking the severity of our climate crisis, but the bill has definitely come due underwater. As these compounding buffering costs, the relentless heat waves, and the corrosive acidification push foundational species like corals and pteropods toward functional elimination, we have to ask, can marine ecosystems and the billions of humans who rely on them for food, economies, and coastal protection actually adapt in time? The changes to ocean chemistry are largely irreversible on human timescales. It's a pretty sobering reality to think about, but understanding these exact mechanisms is the first, absolutely crucial step in grasping the true magnitude of our changing climate. Thank you so much for joining me for this explainer, and I hope this deep dive has given you a clearer picture of the ocean's hidden burden.